So guys, how do we start with this, sir?
I'll begin first with magnetic flux and magnetic induction.
What is transformer? A transformer changes the voltage level on its input winding to another value on its output winding using a magnetic field. A transformer consists of two electrically isolated coils and operates on Faraday's principle of mutual induction, in which an EMF is induced in the transformer secondary coil by the magnetic flux generated by the voltage and current flowing in the primary coil winding. Both primary and secondary winding are wrapped around a common soft iron core. Primary winding of the transformers is connected to the AC power source, while the secondary winding supplies power to the load. As the magnetic line of the force set up by this electromagnet expands outwards from the coil, the magnetic flux forms a path and concentrates on the soft iron core. The strength of the magnetic field induced into the soft iron core depends on the amount of current and the number of turns in the winding. So, when the current reduces, the magnetic field strength also reduces. What is magnetic flux? Magnetic flux is a quantity used to describe the amount of magnetic field line that pass through a given conductor. Given that the formula magnetic flux equals to BA cos theta. B is the magnetic field strength, A is the area of the coil, and theta is the angle between the field line and the normal to the coil. This is an example of magnetic flux. If a surface is placed near the magnet which the magnetic field is the strongest, the magnetic flux on that surface is strong. This is because there are more flux moving through the surface, but if the surface is placed further from the magnet where the magnetic field is the weakest, it will have a weaker magnetic flux compared to the first one, as very little flux is moving through the surface. When the surface is parallel to the magnetic field line, the magnetic flux is zero. It is because the magnetic flux is moving along or parallel to the surface. Another example is when the surface has a larger area. More flux is moving through the surface. As a result, the magnetic flux is the strongest compared to the others. Next, what is magnetic induction? Induction is the ability of magnetic field to create current inside a conductor. We know that electric current can create magnetic field, but can magnetic field create or induce a current? Well, a scientist named Michael Faraday had proven it. Michael Faraday attempted to prove that a changing magnetic field would be able to produce a current. He noticed that a small current was produced in the second coil when the switch in the first coil is turned on or off, but not at other instants. He also discovered that by moving a permanent magnet into a coil, a small current is produced. This also happens when the magnet is removed from the coil. However, no current flows when the magnet is held stationary. When a coil experiences a change in the amount of magnetic flux passes through it, a small current is induced. This is a principle of electromagnetic induction. By looking at the formula, the induced EMF is directly proportional to the rate of change of magnetic flux. The electromagnetic induction happens whenever there is relative motion between the coil and source of magnetic field lines. There is a change in magnitude of magnetic field lines. The area of the coil is changed, and there is a change in direction of the magnetic field strength. The negative sign in the formula means that the EMF creates a current and magnetic field that oppose the changes in magnetic flux. This is also known as Lenz law. Lenz law can be defined as direction of induced EMF always oppose the changes in flux.
Yeah, thanks, Yue. It's very informative. But I think you all will understand better if you know the setup of transformer and principle of operation.
Hi guys, I'm going to talk about the setup of transformer and principle of operation. Transformer is a static device which converts electrical power from one circuit to another without changing its frequency. The transformer mainly works on an AC input because only an AC input offers a time-varying magnetic flux. Here is a picture of a single-phase voltage transformer, where Vp is the primary voltage, Vs is a secondary voltage, Np is the number of primary coils, and Ns is the number of secondary coils. A single-phase voltage transformer basically consists of two electrical coils of wire, one called the primary coil and the other one called the secondary coil. These two coils are not in electrical contact with each other, but instead wrapped together around a common use magnetic iron circuit called the core. This soft iron core is not solid but made up of individual laminations connected together to intensify the magnetic flux through secondary coil. Generally, the primary coils of the transformer is connected to the input voltage supply and converts the electrical power into magnetic field, while the job of the secondary coils is to convert this alternating magnetic field into electrical power, producing the required output voltage. When a transformer is used to increase voltage, it is called a step-up transformer. A step-up transformer has lesser primary coils compared to the secondary coils. When a transformer is used to decrease voltage, it is called a step-down transformer. A step-down transformer has more primary coils compared to the secondary coils. As a transformer is basically a linear device, a ratio now exists between the number of turns of the primary coils and secondary coils. This ratio, more commonly known as a transformer's turns ratio, TR. This turns ratio value indicates the operation of the transformer and the corresponding voltage available on the secondary windings. Turns ratio equals to voltage ratio. This relationship is given as Np over Ns equals to Vp over Vs equals to turns ratio. The ratio determines whether the transformer is a step-out or a step-down transformer. If the ratio is more than 1, then it is a step-up, else it is a step-down. Here are some example questions for you to understand better. Example 1. A voltage transformer has 1,500 turns of wire on its primary coil and 500 turns of wire for its secondary coil. Calculate the turns ratio of the transformer. The solution is TR equals to Np over Ns, which is equal to 1,500 over 500 equals to 3 over 1. Therefore, the ratio is 3 to 1. The next question, if 240 volts RMS is applied to the primary winding of the same transformer above, what is the voltage of secondary winding? The solution is, since TR equals to 3 to 1, which is 3 over 1, equals to Vp over Vs. Since we know that the voltage for primary coil is 240 volts, therefore we can substitute it into the equation, and we will get the voltage for secondary coil, which is 80 volts. It is the end of my explanations, and I hope you all know more about transformer. Thank you.
So now I'll go on with the uses and the applications of the transformers.
Hey guys, I will be talking about the uses and the applications of transformers. Transformers are normally used to increase or decrease the level of voltage in an alternating current known as AC circuit. One example of transformers used for this function is in transmission lines. As you can see, the alternating currents produced at power plants are first stepped up to extremely high voltage, such as 12,000 volt, before being transmitted through the power lines. On the other hand, they will be stepped down to relatively safe values, such as 240 volt before they are introduced into our homes. As for why is the voltage step up, I will explain that later, but for now, I will concentrate on how these voltage are stepped up and stepped down. A step-up transformer would look something like this. As you can see, the number of coils at the primary coil is less than the number of coils at the secondary coil. Hence, this would produce a larger induced voltage in the secondary coil. This can be deduced from this formula. The larger the difference between the number of coils, the greater the difference between the voltage in the primary and secondary coil. On the other hand, a step-down transformer would look something like this. The number of coils at the primary coil is much greater than the secondary coil. Hence, a smaller induced voltage is produced in the secondary coil. Now, why is the voltage stepped up at the power plant before it's been transmitted through the transmission line? As voltage is transmitted, there is bound to be power loss through this transmission. The amount of power loss can be calculated using the formula P equals to I squared R. Since electricity is often generated from a long way from where it is used, it is transmitted through a long distance. From what we have learned, the longer the length of the wire, the higher the resistance. Hence, resistance in a power line tends to be quite high. This will contribute to a huge amount of power loss as heat energy. However, by reducing the current, power loss can be minimized greatly. From the formula P equals to VI, we can reduce the amount of current flowing through the transmission line by increasing the voltage. Hence, this is why step-up transformers are used at power plants to increase the voltage greatly before transmission. For example, take a look at this question. A 5 megawatt power plant generates electricity with a voltage of 5000 volt and a current of 1000 ampere. How much power is lost by sending this current through a 2 ohm transmission line? Power loss is calculated by I squared R, which is 1000 squared times 2, which will give you 2 megawatts. In this case, we would lose almost half of the power transmitted. However, if the voltage is boosted to 5000 kV before the current is sent through the transmission line, how much power is then lost? Using the formula P equals to VI, current can be calculated by 5 million divided by 500,000, which will give you 10 ampere. So, power loss now is actually only 10 squared times 2, which is 200 watt. This amount is really insignificant compared to the original amount, which is 5 megawatt. Therefore, it is clearly seen that by decreasing the current, this greatly reduces power loss. That's all for the uses and applications of transformers. I will pass this over to my friend, who will then present back EMF and the energy issues of a transformer. Thank you.
Yeah, I think there will be some issues about the transformer will be come out in the test, but we don't know anything about that. How?
I know somebody who can help.
Really?
Yeah.
Oh, that's great.
Now, as we all know, the transformer that we've been studying is the perfect transformer. But also, as we know much even better, life is never ever perfect. Same goes for the real transformer. The magnetic flux generated by the first coil over here mostly goes through the secondary coil, but only mostly. Some of them will flow back into the first coil, and since the current going through that coil is AC, then this magnetic flux going back into the primary coil is also constantly changing direction. This will induce an EMF, as we know, through Faraday's law, and through another law, which is the Lenz's law. The EMF induced will be in the opposite direction to the current that is flowing into the primary coil in the first place. So assuming this is the current that flows through the coil originally, then the induced EMF will be in the opposite direction. pardon the dry marker, but yeah. And this back EMF will counteract the original current that comes in the first place, and it will reduce the voltage in the primary coil, which is really not good because when you have the voltage in the primary coil decrease, the induced EMF in the secondary coil is also decreased, which makes the transformer less efficient. And this may seem like nothing in teeny tiny transformers, but in the applications of them, the really huge transformers, this small little reduction plays out a huge factor. The real transformer, like something like how I will show on the screen. This one. In this transformer, the small reduction in voltage becomes very significant. And now, there are always problems in life, of course. I mean, we all know that. And we all wish that they only come in one by one. Unfortunately, they never do. They love to come in a whole bunch, a whole cute little bundle of joy, like a baby. Only thing that this baby is going to kill you. Try to kill you at least. There wasn't only back EMF, but there is also Joule loss through heating. And back onto the whiteboard, as we can see here, deriving the many formulas that we have learned from last year, we have the power formula, which is energy over time, the voltage formula, which is current times resistance, and we have another power formula, which is also voltage times current. So if we through all these variables, we can see that the energy loss is equals to the square of the current times the resistance multiplied by the time. And this, any small increases in the current, the resistance, or the time will contribute to a increase in energy loss. And yes, that also means less electrical energy for something that was supposed to be 100% efficient, damn it. And right now, onto the computer screen, we have hysteresis. Next one. Next one. Yes, here. Okay, this is something probably quite new to us. And in hysteresis, we have we involve the magnetic domains in the transformer coil itself. As we know, every ferromagnetic object has magnetic domains, and when we put a magnetic field through them, they all align in one direction, and this is what makes the magnetic field. So this is great and all, but in the case of a transformer, the current is AC. It constantly changes direction. The magnetic flux also constantly changes direction. So the direction of these domains will keep flipping. So we go back onto the screen. Yeah? Okay. Yeah. We come back to the whiteboard. And this is obviously the best representation of a magnetic domain, don't you think? Well, not really, but it's fine. So in here, for these arrows in bold, these are the direction of the magnetic domains in the original direction. And then when the direction of current is switched, I'll draw that. All the arrows will be pointing in the opposite direction because the direction of the current has flipped. And this will cause the change in size of the walls, the boundaries between the magnetic flux domains. They will also they do that because they have to keep realigning with the magnetic field to be parallel with it, and they will catch against each other. Like let's say there are these two boundaries here. They will squeeze past. They'll try to squeeze past each other. They will catch. And they will snap, and it is this snapping which causes them to lose magnetic energy also in the form of heat. Finally, for the last factor in energy loss from a transformer, we have the eddy currents. So, may I introduce eddy the current? And they are a flow of electrons that go in a circular path within any conductor when a magnetic field crosses through them. So we have the example on the computer screen. Yes. So we have this AC coil here, and for one instance, the magnetic flux will flow around this way. And since this is a conducting plane, we can use the right hand rule to determine in which direction the eddy current will flow. But what we need to know here is that as long as a magnetic field passes through the plane conductor, this current will form, and the current itself will make another magnetic field, as shown here, which will counter the field from the coil. And how this is important in a transformer is that the soft iron core will have its own eddy currents. They'll make their own magnetic fields, which weakens the one produced by the primary coil, and thus lower EMF can be induced in the secondary coil, which decreases the output voltage of the transformer. And so that will be it.